I want to do one of the classic mean value theorem problems. X to the 2/3 has a special place in the heart of all math professors for the reason I'm about to show you. If you let f of x equal x to the 2/3, question is, does the mean value theorem guarantee that there exists a number c in the interval of -1, 1 such that f prime of c equals 0? Well, let's find out. I mean, first of all, the claim, of course, is that there exists a c. Let me put this in a different color. There exists a c such that f prime of c equals f of b minus f of a over b minus a. And in this scenario, it certainly looks like we have a equals -1 and b equals 1. So what that means is that I should be able to write f prime of c equals, let's see, f of 1, 1 to the 2/3 is 1, and -1 to the 2/3 is going to be -1 squared is 1, and then the cube root of 1 is just 1, over 1 minus -1, so that equals 0 over 2, which is 0. So it certainly looks like we ought to be able to find, we've got this 0 here, and the mean value theorem certainly looks like it's asserting that there's a number c such that this equation is true. Let's find the derivative of f prime, and that's going to be 2/3 x to the -1/3. So what we do is we come over here and solve the equation. 2/3 x to the -1/3 equals 0. It certainly looks like the answer is going to be x equals 0, right? No, it's not, because remember that x to the -1/3 is actually equal to 1 over the cube root of x. So if we plugged in 0, we'd be dividing by 0. This function doesn't, this derivative expression that I found doesn't work at x equals 0. Recall that the mean value theorem says that the function has to be continuous on the closed interval ab and differentiable on the open interval ab. This function is not differentiable on the interval -1 to 1 because it has one point where it's not differentiable. To be differentiable on an interval means that you're differentiable at every single point in the interval. I know that there are an infinite number of points in between -1 and 1. If you consider all the real numbers, there are an infinite number of them. So what difference does just one little point make? Let me show you. I'm going to graph this function. So this is the graph of y equals x to the -2/3. And see how it has this point here predicted exactly by this expression. We can't plug in 0 because the function is not differentiable at 0. It has a point that looks like a classic situation of being not differentiable. It's a corner instead of a smooth curve. So look what happens here. The mean value theorem is predicated on the idea that the function is turning smoothly. Like if I were to graph a function that looks, let's say, like this, nice and smooth, I can certainly say that it takes on every possible slope on its path from one end to the other. That's because the function is very nice and smooth. But here the function turns a very sharp corner. It's sloping downward, it's sloping more, it's sloping more, it's sloping almost vertical, and then look what happens. It just very abruptly turns around. So it never maintains that smoothness. It's possible for it to pass completely from this slope here, a line that looks like this is a very steep slope. Let's say that that's like -1,000,000 slope. It's able to pass in one point right from -1,000,000 up to a slope of +1,000,000. So it never, the non-smoothness of the function, the fact that it's not differentiable and has that corner, allows the function to turn very, very sharply, thereby defeating the whole point of the mean value theorem, which is that the function has to pass through all the possible slopes, eventually settling on one that's equal to the slope of the secant line passing through its endpoints. So even though what we had here is that's -1 and that's +1, and this has a horizontal line, this function, by virtue of its corner, never has to pass through a phase where it has a horizontal tangent. So that's one of the reasons that x to the 2/3 is considered one of the most important examples, really counterexamples of the mean value theorem. Not counterexample of the theorem, but rather an example where the theorem does not apply. That's a better way of saying it.